Okay, so this is the Unit 3 review. And so this first part was talking about the history of the atom. And so you need to be aware of the scientist, what was kind of significant of their model. You need to be able to identify what their model looked like and sequentially their order. You don't need to know the date, but you need to know, kind of the chronology, the oldest to the most modern. Okay, so this was the first model. Really, it was come up with Democritus, this Greek philosopher that was 400 BC. And then later, it was reintroduced by Dalton. You'll notice this. But basically, what they thought, atoms were small solid spheres, so there were no parts, they were just one whole thing. Democritus actually coined the term atom because atomos in Greek means indivisible, not invisible. Indivisible cannot be split. They also thought that all atoms of a given element are identical. Okay, the next major one was going to be Thomson, so J.J. Thomson. And so Thomson came up with this idea of what's sometimes called the plum pudding model, where you had the entire atom being positive, and then you had these little negative particles, these electrons spread throughout. So it's like blueberries in a muffin. He came up with that by using a cathode ray tube. And so that's kind of what was important with Thomson's model. The next one was going to be Rutherford's gold foil model. Okay, and so what's different about this, notice Rutherford, you have the nucleus here, and the nucleus does have a positive charge, and the electrons are all outside of the nucleus. And so Rutherford, he used this gold foil experiment where he shot alpha particles that were positive at a thin film of gold. Most of them went straight through. And so he said, well, the atom's mostly empty space. Occasionally, some of these alpha particles would be deflected slightly to the left or the right. He knew that the alpha particles were positively charged, so therefore, that meant that there was a concentration of positive charge somewhere in the atom. And on occasion, a few of those alpha particles ricocheted straight back towards the source. And so he knew that what he hit was extremely dense. And because he almost never hit it, he knew it was really tiny. And so Rutherford's model, tiny dense center called the nucleus, where essentially all the mass is located. That nucleus did have a positive charge. And then most of the rest of the atom is empty space. So a lot of volume where the electrons are, but not a lot of material, not a lot of matter. Okay, the next model is going to be the Bohr model of the atoms. That's sometimes called the planetary model. So you look at it, you notice that the electrons have organization. They exist in specific rings, kind of like planets orbiting the sun. Once again, he didn't know about there being parts of the nucleus. He knew that, there was just that positive center. And he knew the electrons orbited around that nucleus. He also knew that the electrons could move from energy level from one to another, so they could either absorb or release energy to be promoted to a higher energy level or release it to fall down to a lower. And this one was kind of the modern atomic theory. And so there's lots of people that were involved in this one. So like Chadwick discovered the neutrons that are in the nucleus. You also had like Heisenberg and Schrodinger. Those guys were really responsible for this idea of the electron cloud, and de Broglie is another one. So this is kind of our modern understanding of the atom. So protons and neutrons in the nucleus, the electrons existing in the cloud, and you might see the cloud like this. Maybe you'll see some of these, kind of these barbell kind of shaped things. It could be something like this. So numerous types of ways you can demonstrate the electron cloud, but that's pretty much the modern atomic theory. Okay. Next part is talking about completing the following table. And so in looking at this, so if I have 8 protons, what else has to be 8? Well, that has to be the atomic number. And it looks like I didn't put a place for the atomic number on here, so that's fine. But you also know that looking at the periodic table, the atomic number, so if I have 8 protons, that element is going to be oxygen. And so oxygen goes here, and the atomic number actually goes as a subscript to the left-hand side. If I tell you the mass is 17, that means this particular isotope has a mass of 17. Well, I know the protons and the neutrons add up to be the mass number. And so 17 minus 8, this tells me that there must be 9 neutrons. So 8 and 9 will give me a mass of 17. The mass is written as a superscript to the left. Normally, if the electrons aren't listed and there's nothing indicating this thing has a charge, it's going to be a neutral atom. The protons and the electrons will be equal. Okay, so that's 8 electrons. And so the symbol here is oxygen. And then if you were going to write this, you write the name oxygen, then -17, the mass number. Okay, this next one. Okay, we have strontium here. Strontium, because I look at strontium on the periodic table, notice it has an atomic number of 38. That tells me it has 38 protons. Okay, if I happen to have 38 protons, there's probably 38 electrons, unless there's something telling me different. Okay, and so in looking at some of these things, if the neutrons are 62, summing these two together, 38 and 62, mass would be 100 in this instance. So I go to write this, I'm going to put SR 100 and 38. And so this is strontium 100. I'm going to do just a couple of extra ones. These are not ones that were on your review, but just to kind of make certain we're aware, I'm going to demonstrate a couple of what are called ions. Okay, so let's continue this down. Let's put this like a couple more things on here. We'll do a couple. And these weren't on there, but it's just a good little review, and this is something you should know. Okay, so let's say I give you something like this. Let's say I give you, for example, let's do this. Let's say I give you a symbol. Okay, a nuclear symbol, and let's give you, let's say N, and I'm going to say 14,7, and let's say I'm going to give you 3 minus. Okay, now this is a little different because this one demonstrates that I have a charge. That's going to affect the electron number. The other things like this is 14 because the mass is located there. Atomic number is 7, so I have 7 protons. Neutrons, 7 and 7 make 14. Okay, so this is just nitrogen, -14. Now what's different here, notice I have a net charge of -3. That means I have 3 more electrons than protons. So electrons are negative, protons are positive. So since I know that I have 7 protons, if this is a net charge of 3 negative, that means I have 3 extra electrons, I have 10. Okay, so that's one way you could do it. I could also do something, here's another example of another ion. Let's just do this one here. Let's say maybe I give you the information. Let's say maybe I tell you the protons. Let's say I give you 20 protons, and I give you 20 neutrons, and let's say I give you 18 electrons. Okay, well, the mass 20 and 20 would be 40. Okay, well, and this happens to be calcium. So I'm going to write calcium -40. Okay, when I go to do the symbol Ca, 40 goes up here as the mass, 20 is the atomic number. Okay, notice I have 20 protons and I have 18 electrons. I have 2 more protons than electrons, 2 plus. Okay, so the main thing I want you to be aware of, if you're going to be doing an ion, it has to be very specific. I either have to A, give you a symbol that has a charge on it, or I have to tell you a number of electrons that is different than the number of protons. If one of those scenarios is not true, that is a neutral element. Okay? All right, let's look at the next part. So we're completing the subatomic particles, and so we're just going to label these. We have the atoms are made of protons, neutrons, and electrons. Okay? So both protons and neutrons are found in the nucleus, in that tiny dense center. And then the electrons are found out in the electron cloud, or you could say orbitals, energy levels. Okay, I don't care, but they're out in the cloud. Okay, looking at their charge, protons have a positive charge, electrons have a negative charge, neutrons are neutral, they have no charge. In looking at their masses, both protons and neutrons have a mass of 1 AMU. Electrons effectively have no mass. They have mass, but man, it's tiny. It's 1/2000th the mass of a proton or a neutron. And so that's something that, is essentially massless. All right? Okay, and looking at this one, so on the fourth problem, we were to complete, this is dealing with some electron configuration. And so I'm going to demonstrate the electron configuration, the orbital filling diagrams, and the shorthand or noble gas configuration for these elements. So if I look at phosphorus in its location on the periodic table, its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p, and it's the third one over. If I were going to draw an orbital filling, anytime I draw an S, I draw one line. And then these are the two electrons demonstrating opposite spin. Whenever I have a P, I draw 3 lines. So here's 2P. Notice how they fill. They half fill with a like spin before they pair up. So it goes up, 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 down, down, down. Here's 3s2. And then when I go to draw 3p, here's 3p, and it goes 1, 2, 3. So that is the orbital filling diagram for phosphorus. If I'm going to do the noble gas configuration, I find the element, I go back to the previous noble gas. I go back, and the previous noble gas for phosphorus is neon. And then basically I start from that point. And so it's going to be 3s2, 3p3. So that's the 3 electron configuration types there of phosphorus. Okay, we're going to do another one, this time with zinc. Okay, so same type of deal. Zinc's electron configuration goes 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then remember when we get into the D block lags one behind. So even though we're filling the 4s up there into calcium, when we go into that D block, it goes back down to the 3D. And so scandium is 3D, and it happens to be the first element, so it is 3D1. If I draw an orbital filling, it looks like this. 1s2, 2s2, 3 lines for a P. I'm going to go 1, 2, 3, 4, 5, 6. Here's 3s2. 3 lines once again for the 3p, labeling the middle one. 1, 2, 3, 4, 5, 6. 4s has 1 line. There's 4s2. Anytime I do a D, it's 5 lines. So I label the middle one 3d, 1. It should look just like that. That is zinc's orbital filling diagram. And then last, we need to do the noble gas configuration. So I find zinc, I go to the previous noble gas, I place it in square brackets, argon, and then I just start from there. So it's simply 4s2, 3d. Oh, you know what? I wasn't paying attention. That's zinc. Why was I doing scandium? My goodness. It's zinc. Why didn't you tell me? That's 3d10. It's all the way over in the D. My goodness, I'm glad we caught that. Too bad I can't go back and fix the video because I don't have the editing software. There's 3d10. My goodness, there we go. I caught it right at the end. Well, good for me. Hopefully you weren't screaming at your iPad. Okay, that's it for part 1. We'll continue on here in part 2.